All right. Now, these trig equations, what we call these, and the directions kind of say something about them here, is they're what you call ones that are in a quadratic form. Okay, so let's see if you can kind of spot what I'm talking about. So, like in regular algebra, what do quadratic equations always have in them? Right, a square. So in this one, you've got a sine squared, and then a regular sine, and then a constant. So like the quadratic term, the linear term, and the constant. So it's a quadratic form. Okay, so it's going to be real similar if I solved an equation like this. Let's just do an algebra equation first, like x squared minus 3x minus 4 equals 0. So how could I solve something like that? Factor it, yeah. So like factors of 4 that subtract to be 3 would be 4 and 1. Right, they're going to be different. That one's going to go on the bigger number, so it would be minus 4 and plus 1, so you would get x to be 4 and x to be negative 1. Okay, now what we're going to do with this is real similar to what we're going to do with the trig form that's a quadratic form. Okay, now to make it easier to factor, we're going to do that substitution thing. Okay, so we're going to substitute here. We're going to let a be equal to sine x. Okay, and what it's going to do is it's going to knock the equation down to something that's more like algebra than trigonometry. So it's going to go from trigonometric to algebraic. Okay, yeah, so it makes me sound really smart. Now, so watch. If we make a equal sine x, how can we write? That's 2a squared plus, and then this part would just be a. And now if we look at this, we can solve that a lot easier, can't we? It's a lot more doable. Now, it's not as quite as easy as this equation because this one didn't have a leading coefficient. So we can still factor it though, can't we? If we got a leading coefficient, that just means we need to split that middle term. Okay, so instead of factors of 1 that subtract to be 1, it's factors of what? 2 that subtract to be 1 would be 2 and 1. So 2a and 1a. Right, now signs are going to be different. It'll be plus on 2, minus on 1. All right, let's bring this down. So we split it, and now what? It's different from like this one over here. Yeah? What? Group it. So out of these, we could factor out a 2a. That'll leave me with a plus 1. Okay, and then out of this group, negative 1, so that'll leave me with a plus 1. Same thing. Okay, and now I can factor out the a plus 1, and that'll leave me with 2a minus 1. So we'll get a to be equal to negative 1. And then what about this one? Right. Now, that's the algebra form of it. Now we got to go back and solve the trig form. So what was a? Sine x. Okay, so we get now sine x equals negative 1 and sine x equals 1/2. Okay, so now notice what they don't have on these that make them real nice. They don't have coefficients on x, do they? So none of that stuff where we got millions of solutions. Okay, just few nice solutions here. Where's sine negative 1 at? Yeah, okay. And where's sine 1/2? Pi over 6 and 5 pi over 6. Got 3 solutions there. Okay, so normally students kind of like these a lot better than the ones when you have coefficients. I like the quadratic formulas. Yeah, I told you. they're kind of fun. Now, let me look at 42. 42's even easier. Okay. All right. On 42, what do you notice about this one maybe that's going to be a little easier here? Yeah, no leading coefficient. It's going to have to split and group. Now, let's do our substitution thing. So we're going to let A equal cosine x. Okay, so that'll make it say a squared plus 2a minus 3 equals 0. So now factors of 3 that subtract to give me 2 would be what? 3 and 1, right? Now, and I don't have to split, do I? Factors of 3 that subtract to be 2, 3 and 1. And I don't have to split on this one because I don't even have a leading coefficient. So let's see, my signs are going to be different. It'll be plus 3 and minus 1. So we're going to get A to be equal to negative 3 and 1. Now, there's something aside here that I needed to say on this one, and it's actually kind of a good thing that comes out of this. What we really do here when we say cosine x equals negative 3 and cosine x equals 1 is we're finding the inverse. Okay, we're using inverse cosine. So aside, when I had like inverse cosine of theta, what did we say here about when this was like equal to y? What did we say about the domain here of theta? Had to be in between negative 1 and 1. Remember that? That's not that big of a deal, okay? But this value here has to fall in between negative 1 and 1. Now, negative 3 does not, does it? So what's going to happen is this is not going to give me any solutions. Okay? The negative 3 is not. So I just don't have to worry about it. So anything that doesn't fall in between negative 1 and 1, I'm just going to just do away with. Now, what about 1, though? Yeah, that falls in between them. Okay, so A is equal to cosine x. And so where's cosine 1? 0. Now, you say 2 pi. Right, but what do the directions say? 0 to 2 pi, and it has a parenthesis. So if it had the bracket there, we could say 2 pi. But we'll just say 0 here. Okay. Now, let's look at another quadratic form here that's a little bit different. Okay, so like on 48, what do you notice there? It's different. Right, it's 2 instead of 3, and what term is sort of not there? The linear one. Right, sine x term, okay? So it kind of compares to an equation maybe like this. What if I have like 2x squared minus 6 equals 0? We don't really need factoring to solve that. We can just solve it, right? Wait, take the 6 over, then what? Divide by 2. So that's 3, and then we take the square root of both sides. But right, the plus or minus is important. We'll need that. So it'll be plus or minus square root of 3. So we can do the same thing with this one since it doesn't have the linear term. Now, some people still like to use that substitution thing. I think with these, you really don't need it. You just still solve it. Like the substitution idea, let A equal sine x. But I don't do that on these. So I'm just going to add the 3 over. So I get 4 sine squared x equal 3. Okay, now what though? Alright. So we'll get sine squared x equals 3/4. And then square root. Now we got to do the square root of fraction. So I'm going to like get mad and cry and go home. No. I'm going to do the fraction. Just do the numerator and the denominator. And it works out pretty good in the denominator, because that's just going to be 2. Oh yeah, square root of 3 in the numerator. Okay, now, this is where I'm afraid you'll mess it up. Hang on. Plus or minus square root of 3 over 2. Okay. So now, where is sine square root of 3 over 2 or negative square root of 3 over 2? So lots of spots there. Yeah. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3, me pi over 3, okay, u pi over 3. All right. So all of those. Okay. Now, 50 is another one that's kind of similar here. Am I right? Where we use the square root method. Do y'all want to do number 50 or are we good here? You want to do it? Okay. Now do me a favor because I don't have it in front of me. Call it out. I mean tangent squared. Okay. So now we would add the 9 over first, right? And then divide by 3. So we get tangent squared x equals 3. Now we're going to take the square root of both sides. So we'll get tangent of x equals plus or minus square root of 3. And so where is tangent plus or minus square root of 3? Lots of spots. Yeah, it's all those pi over 3's again. Okay, pi over 3. Same thing as the last problem. Alright, the tangent at pi over 6, Katie, is square root of 3 over 3. Write it on the unit circle. The tangent at pi over 6 is square root of 3 over 3. Okay, and the tangent at pi over 3 is square root of 3. Yeah, good little pattern there. All right, this one. So we also would have 4 pi over 3 and 5 pi over 3. All right. Now, I did change that yesterday. I think I had 39 to 51 odd. I backed it off to 49 odd. And then the one little calculator problem to review.